Hello guys. I wanted to take some time today to reflect on where I've been and where I've come. And then do also a Leetcode problem. One or two Leetcode problems, I think. Later in the day, I also want to focus more on my own tasks. But happy Boxing Day. At least that's what's happening right now. Happy Christmas, as it were yesterday. And we will see and talk about today. One thing for sure is that I just need to rearrange some things. There are a lot of things that I want to do. A lot. Maximum subarray I want to revisit. But then do another Leetcode problem as well with it. So in order to actually give myself an idea of what to do today, I just got to write a list. The problem is my list is currently kind of messy. Fuck it. Fuck it, I'll just share this shit. There is a lot on this to-do list. However, let's move this all to the evening and consider some other tasks. All right, so one is obviously Leetcode. We're going to move that out. We're going to do, let's see, a little reflection on one's self. I'm going to have lunch. I'm going to have dinner out. Yeah, I have dinner out. Oh, that reminds me, I gotta throw something out from this bag. This is actually really bad that I kept it here for so long. To be honest, I have a lot in this bag. Okay, I gotta clean this out at some point. Doesn't matter that there's a really let me just clean it up. Been in my bag for too long. Gone for my Well. Now. Okay. Room cleaning is going great. Ooh, actually. Vitamin D tablets. Because I lack sunlight. I lack touching grass. Cool. Feed. Okay, so this is kind of like, I don't know if you can see this, but this is like an AWS bag. Why do I need this? For when I want to buy shit. So I'll probably have this. Like lots of stuff in here, by the way. There's like, ugh, so many stickers. They're just thrown into one bag for me. People that gave me this bag also threw all this stuff in it. Anyway, take this bag, use it as like grocery shop. Hold this up, huh? Customer obsession. It says on the bag. Okay, all of this stuff, like stickers, stickers, stickers. I don't know what these actually mean. But I'm sure there's some significance to these stickers. But regardless, I don't need these. I don't need these myself. Figure out what to do with these. What is this? Leetcode Academy? I think it is. It's like how to get into these companies. We've got some people from like data engineer at AWS, full stack developer. Somebody at Canva, DevOps engineer. Sorry, DevOps at Atlassian. Okay, well, This is still like good stuff that I kind of want to. Not gonna lie, kind of want to keep. Making sure there's nothing else. Sorry, let me put this. Um, tag. Finally. Okay. I got a lovely sock. Shout out to you. You know who you are. Okay. I will. Headphones on. Not that I actually need them on. I'm trying to think how to organize my station. I want to keep a photo of this before I throw it. So, to be honest, I'll keep this here. Alright, now we can focus on something, I think. So, I said dinner out. I think that's what I will do. Lunch in, or do I go lunch out? I could buy lunch and then eat dinner. That could be an option. Very plausible. Very, very plausible. I might buy, alright? But fuck. And then we'll eat dinner. So lunch out, lunch Uber, eats. I'm like, that's funny as fuck. That's funny as fuck. I don't think I should search it up here, to be honest. But I think that's what I'll do. Ooh, I do need to like work out, right? That's one thing I do want to do also. I want to consider dinner. After dinner would probably be just chilling, but there's some other stuff I want to consider as well. But I think if anything, we got to do some Leetcode problems. We're gonna have a look. We're gonna in the afternoon do some reading of the design doc that I'm writing. I think it should be good if I do just look at it at least once over. And let's see. So that's mainly it, I think. I'll now look at try and processing some of this into my head. Kizetsu, good to see you. Good to see you too. Happy holidays indeed, right? Happy holidays indeed. It is very good. Hope you've had time with your family and chilled. Okay. Now, perhaps I want to try these. You know, somebody's 30 push-ups, normal, diamonds, and then wide. So then it becomes like 90 push-ups, right? And then, wait, 3 sets each. What the fuck is 3 sets each mean? 60 dips, 60 squats. Fuck it, regardless, this is what I'm doing, alright? Fuck it, regardless, this is what I'm doing. I'll take this, mark it as done, put it here for now, but it also means going into Obsidian and putting it there. I'm gonna put it here. Workout strategy by a viewer. Alright. If anything, I also need to like make this recurring, but it's alright. Yeah, let's just make this recurring. Alright, so repeat after completion, 1 day, add reminders, nope, add deadline, nope. Okay. Alright, workout, things to buy, video editing. So I was thinking of making some videos, right? Something I want to do. And if there's time and I feel like it today, I will write something or do something. It's also a question about, you know, what to do. That's also very, very of concern in terms of that video. I was thinking of making a TikTok on, you know, what I've done this year, or like a short form content where what have you done this year, or what I have done this year. Make new friends, do Leetcode. These are some ideas that I have. So this is like a little reflection on oneself. Buying, right? This is buying stuff to buy. Right, so this is just like not necessary to know. These go down, internship, subject thinking. Like I'm always thinking about this at the moment, so I'll take that off. This is a video. This is an email that I want to read, but this is probably going to come when I get back to Melbourne. So by that time, the time that I'm back in Melbourne is basically the 24th. Okay. And these were just some ideas that I had. Maybe I'll just write them down here instead. Right, so if we had some ideas, right, on why to get a 9 to 5. Right. This idea I want to centralize in another note. I wonder if I can actually find. Oh. And put it here. And I'll make these like. Oh, like a to do. Yeah. I guess yeah, the main idea that I want to get across these points. I'll take that off. Mindset that changed my life. I wanted to do this because I saw, like, I got inspiration from the video. Someone had something like that. Layout. give back. So these are just things to consider when time comes. I guess these will always be here. I'm fine with that. These things I want to do, but we're gonna go put these into 24th because we're just not gonna worry about it right now. These things I also got to do at some point, but I'm literally gonna push it off up until the 24th. Bit warden best practices also gonna move that to the 24th. Okay, yeah, no, we don't need to do this. So this is like the list for chicken wraps. This is to buy, give back. Okay, so these are just like docs, and I shouldn't ideally put docs here. But as it stands, this is where I do put stuff. I should move this though. I should put it in like in its own safe space. Yeah, I'll put it in its own safe place. Meh. So we're gonna cross these out. And then say, let me think, layout, give back. Like these are stuff that I think about. These are things that I think about from a docs type perspective, So I'll just create a new list for docs. All right. I shouldn't ideally have something like this. What am I saying? I ideally should not have something like this, I guess. But I call this documentation. Life documentation, I guess. I like life documentation. As such, you can put this as any time, but it's documentation right here. Alright, and then these are the things that I want to do. Alright, that's it. That's it. We cleaned it out. We cleaned out our to-do list. And this to-do list, by the way, it's literally been almost a month that I've actually spent the time to clean this to-do list. So it's good that it's now cleaned. And we can focus on something more honed in, right? Yeah. Let me think. I also want to make a video on like what I've learned, or like what's a good title? Let me think of a good title. For my time at Amazon, because that's also something I'll think about. Like, I need a good title for my Amazon internship experience. Let's just call it my Amazon internship experience. Let me think. Yeah, why not? My Amazon internship experience. But yeah, it's not going to be as transactional. We're going to make it more, me. Something like this. Okay. Regardless, this is kind of the order in which I want to do the videos anyway. I also got to collate all the footage that I have so far. And by collate, I mean download them all. Let me think. Yeah, I have to do some like need to get some footage. I need to do. This also can I put kind of close. Maybe I'll just put it. Sorry, this is the fan next to me. Oh, you guys would hear like a. Okay, actually, that's kind of bad. I'll just turn this off. I don't need it. I don't need it at the moment. Okay, after lunch, I got a shower. I gotta look at Design Doc. Amazon. So technically, you know, a little reflection of oneself is going to be this. Take this. Technically, I've kind of done a little. Actually, looking at my to-do list. Video editing, we're going to say. Let's see, footage collating is something that I do, and then video editing just after that. Yeah, that's kind of looking like how the day will progress. Let's see how it goes. Can do. Given that it's already 10:36, I want to pre-plan what food to get. So give me a sec, because I want to do this on my. You can still hear me while I. And hello, George Vell. Merry Christmas indeed. You've enjoyed time with your family. Ooh, I gotta charge my watch as well. Getting low. Okay. Nice, and we're just gonna put the. Okay. I'm just gonna buy something for right now. Interesting. Chili chicken pizza, $30. Wings meat. Naked burrito. Mm-hmm. Wow, the choices are hard to choose, isn't it? Look at all the offers. Hmm. Cheese pizza. There's a wrap that I could get. Oven roasted chicken. Wow, there are inside. I feel like the wrap is big, is it? Crisp lettuce, fresh tomato, and pepper protein on a and well, the thing is, we need chicken. Hot pepper chicken. Spicy. Maybe I do like my spiciness. Okay. Gluten-free wrap. And there's a lot of options. Fuck it. We'll see. We'll see what it's like. Yeah, we'll see what it's like. Hmm. Probably pretty big as well. We will see. Let me just order this now as well. Um. hmm, How do I order this? Oh, there we go. Schedule. So today at I'm gonna say 12 to 12:30, 12:15 to 12:05. All right. Fuck it. Um. Okay. I'm done now with that. Um. Time to get back. All right. So now I've organized quite a lot. Oh, the camera and camera. Alright, I know what to do. Be right back. Okay, I'm back online. Okay, I already did this now. Alright, let's do some Leetcode problems. Let's get on to that now. Because we're gonna focus. Okay, the maximum subarray problem. I don't know if I'll remember, but we will do it anyway and we'll see. Okay. Let me try and think. I'll close this. Make this into a third. Close that. Keep this here, I guess. Doesn't hurt. And we'll go obsidian. Place it on the right side. Back, go back. I got maximum subarray. That was the problem there. Okay, we're just gonna hide it for now. And try to think about the problem as if it were a new problem altogether. Okay, so the problem is, given an array of integer nums, find the subarray with the largest sum and return the sum. A subarray is a contiguous non-empty sequence of elements within an array. A contiguous non-empty sequence. In which case, so if you have nums of equal to 2, -3, 4, blah blah blah, then you get an output of 8, because if you think about it, you have 4, -2, 2, 1, -1, and 4. Then you have the nums equal to -1, then you would output -1 because that's the largest sum. So maximum subarray. Find the subarray with the largest sum and return the sum. Right, so that's what you gotta do. You gotta return the sum. Now, how do you go about it? Alright. One thing I gotta do also is just think about keeping myself upright. I need to keep my back straight. I've had a problem recently with keeping my body straight. Okay. Let's just try and keep my body straight now. And then we'll see what we can do here. Alright, let's think about this problem first. Firstly, I don't see how this is greedy at all. I totally forgot what Kadani's algorithm is, also. Kadani. Or I should say Kadane's algorithm. Although I should try and remember. So if I've forgotten, I'm just going to probably look at what Kadani's algorithm is. So let's open this up. I'm pretty sure though that's basically going to solve the problem for us. So in the maximum product subarray and maximum subarray. Let's have a look at Leetcode here. Because why does it feel like I wouldn't have made so much effort to do these types of problems if I hadn't done them already on a Leetcode problem? So I did these a month ago. Coin change. When was this? 4 weeks and 1 day ago. This was right before I left. Did I speak about this? I feel like I did. To someone. And maximum product subarray. DP problem straight up. I'm sure then it must have been like a DP problem. Alright. Doesn't matter, let's do this. The Katani's algorithm, looking at this, alright, so I just solved this problem in basically less than 5 minutes after having already known the solutions from maximum product subarray. Katani's algorithm was useful here, so maximum product subarray. So brute force is O of n squared, and the method I was thinking of originally. The problem can be solved using sliding window with time and space complexity O of n. Kidani's algorithm is the bottom-up dynamic approach that solves in O of n and O of 1 space. Then there's a prefix and suffix which takes O of n time and O of 1 space. Try implementing Kidani's and then prefix plus suffix. I see. This is coming back to me. So this was my DP solution for that problem. Was this a 2D dynamic programming problem? It kind of looks like it, right? But I guess it's still 1D maybe. Since the above is not random access, you can make this better so that it is on space as per Kidani's algorithm. The part that I want to think about is also why I did this. Yeah, it is maximum product subarray. And so as a result, I did maximum subarray. Yeah, I remember now. I was like, alright, if I do maximum product subarray, then I'll also do maximum subarray. So, alright, let's remember how this solution was done. So, the max subarray right. So those are the two choices, to include or not to include. And so the result is just keeping track of the maximum possible subarray. I see. I can understand that. Now, maximum product subarray. the DP solution was this, whereby what is the 0 and what is the 1 here? What was my thinking here? The product? There was something about like, there was something about this. You gotta keep track of a max and min. Because when you keep track of the max and min, when you have a product, it's kind of iffy. Right, so min max. I don't know why it's just funny. Okay. Sorry. I was kind of cringe. Alright. Alright, but maximum subarray using this DP. I don't see how this becomes greedy at all in any case. Right. But let's now see the solution here. So the brute force, why is that important? O of n squared, space complexity of O1. 2 of n. N squared. Yeah, but that's worse recursively. Recursive is worse. So it's just way worse by doing a recursion way. And then a dynamic programming top-down approach is, I guess, a good extension of the recursion. And then a dynamic program bottom-up is the same, just it's bottom-up. And then you can have a space-optimized approach. And then Cardani's algorithm. And then divide and conquer, sure. N log n and log n. I guess that's just like if you really want to look about it that way. Alright, let's look at this.
Let's solve Leetcode 53 maximum subarray. So we're given an integer array of nums and we want to find the contiguous subarray containing at least one number which has the largest sum, and then we want to return only the sum. So this array has positive numbers and it has negative numbers. So that's what we have to keep in mind. In this case, the largest sum is 6, and it's just this middle portion of the array. So the first thing you might try is just compute every single subarray, right? So let's first compute every single subarray starting at -2. There's one subarray, there's two subarrays, there's three subarrays, and then we keep doing that until we got to the end, right? And then we could repeat the process for the second number. So the subarray starting at 1 here, another subarray starting at 1 here, another subarray starting at 1 here, all the way until the end. Now we could repeat that same process for every number in the array. So let's just write the pseudocode to see what kind of complexity this would yield. So let's say we're starting, the I is going to represent the starting value. It's going to range from 0 all the way to the last number, n minus 1, or the last index, n minus 1. And then we want to get the ending index. So I'm going to use j for the end of this subarray. So we're going to start at I, and we're going to keep going until the end of the subarray, or until the end of the entire array, n minus 1. So this represents the start, I represents the start, j represents the end. Now we actually want to compute the sum of this subarray, so we're going to have a third loop for that, right? Let's use k. K is going to range all the way from I to j, right? Because that's what represents the subarray. And then in here, we'd compute the sum, right? Now, obviously, this is really inefficient, right? The time complexity is n cubed. It's obvious because we have 3 for loops. So let's try to expand upon this. Let's see if we can make any shortcuts to improve it. So the most obvious thing you'll probably notice is that we can save time when we're computing a subarray. So if, let's say we computed this subarray, right? And then we want to compute the next subarray with just one added element. Well, we can save the result of this, right? And say it's our current sum or whatever. And then to compute this subarray, we just have to add this number over here, right? So we can just say current sum plus -1. And so this can save us time. Let's take a look at the time complexity of this solution. So we're going to have another for loop, which is going to represent the start. So start is going to range from 0 all the way to n minus 1. And we're going to have another loop for the end of the subarray. J is going to range from I to the last index, n minus 1. And then inside of the loop, we're going to maintain our current sum and simply just add the number j each iteration of the loop, right? So this is a little more efficient, O of n squared. It's a pretty easy optimization to make, and it improves your solution a lot. But can we do even better than this? So now the question you should ask yourself is, do we have to compute every subarray starting at every single value in the array, right? Do we have to start at every single value and compute every subarray that comes after it? I don't think we do. Remember, we're trying to find the maximum subarray. We can use that knowledge to help us make a shortcut. So let's take a look at this. We have a -2, right? So when we're starting here, that's going to be our max sum so far. Then we get to -2 plus 1. So this is -1 so far, right? Do we actually need this negative number? The negative numbers don't contribute anything in this case, right? So we can basically ignore that value, right? Once we get here, we can basically say this negative value, this negative prefix that came before +1 isn't going to help us at all. So let's not even consider it. So next we get to this -3. Now up until here, our total sum is -2, right? So then we get to this 4. This is a negative prefix that came before it, -2, right? So we can say up until this point, we're not even going to consider what came before. So this 1 and -3 aren't going to help us at all. Just ignore them. Now we get to a -1. So the prefix that came before this was a +4, so we're going to not delete it from our list. We're going to keep that +4 and add it to this -1. So now we're going to be at 3 so far. Now we get to a +2, right? Even though there's a -1 that came before it, well, there was a +4 that came before that. So if we get rid of this -1, we also have to get rid of the +4, which we don't want to do. Remember, we have to keep the subarray contiguous. So I'm not going to chop this portion off. I'm going to keep it. Now we're going to add 2 to it, so now we're going to be at 5. Then we're going to get this 1. We're going to add it and get our subarray of 6, and this is the result so far, but let's keep going and see what happens. Next we'll have a -5, right? So -5, now we're at 1. So obviously we decreased our subarray, but we know this -5 is not going to be deleted because we had a +6 portion comprised of these 4 elements that came before that. Lastly, we get a +4 again, add that, our sum is still 5. So we see that the max subarray was this portion of these 4 elements, which totaled to 6. Now, this was a linear time algorithm. It's kind of like a sliding window, right? We keep incrementing our right pointer as we go through the array, right? But our left pointer keeps getting shifted if we ever have a negative prefix like this -2 or this -2 portion comprised of these two elements. So anytime we get a negative prefix, we remove it. And for me, it kind of helps me to think about this as like a sliding window. And since it's a linear time algorithm, the overall time complexity is big O of n. We didn't need any extra memory. We just had to go through the array, removing any negative prefix as we computed the total sum. Okay, so now let's code it up. So we can initialize our max subarray to the first value in the array. That's like the default value that we're going to give it, because we have to give it something, and it can't be 0 because we know we have negative values in this array. And we know the array is non-empty, so the 0th value of the array is always going to exist. And we're going to be constantly computing our current sum, so I'm going to initialize that to 0. So let's go through each number in nums. Now remember, if we had a negative prefix, we're going to remove that portion from our current sum. So the way that we can check this is just check if current sum is at any point negative. If it's less than 0, we're just going to reset it back to 0. And then after that, we can add our current number to this.
Okay.
This will make sure that we're always computing the maximum that we can.
Sure.
Now this current sum could be the possible maximum, so we're just going to update our max subarray to the maximum of itself as well as the max that we just computed.
Right. Sure.
After we're done with that, we'll return whatever we computed as the max subarray. I hope this helped show you kind of the intuition behind the solution of this problem. If it was helpful, leave a like and subscribe, and thank you for watching.
So what was his solution just now? It wasn't even any of these that he had. That's all right, I get it. Let me do it in not the Leetcode approach. Oh, oops, let's see. Let's do it in Kedan's algorithm. All right, we're gonna have a result. It's gonna initialize to 0 originally. We're gonna have we're gonna keep a DP. So we're gonna keep a DP, make everything maybe 0 at the beginning. So I might just do it like this. Say 0 at the beginning times nums. Nums, I should say. Right, for I in range nums. Right. We gotta think. The DP of set I could be 0. Is gonna be +1. And you go from 1 to here. And this is equal to dp of I minus 1. So this is a plus, right? Plus nums of I minus 1. Right? So it's either this, if dpi minus 1 plus nums I minus 1 is greater than dp of I max dp of I or res, else dp of I is just equal to dp of I minus 1. Alright. Yeah. I put 13. I put 0. Yeah, for sure. Good. Good. Instead of calling it 0, it's none. Yeah, there's something wrong with this thinking. Okay. Okay. Think about the subproblems. Think about the subproblems. Alright, so if you have a subproblem of just say in this example 2. What's the maximum sum? 2. And you think of this subproblem, well, what's the maximum sum? Is it 2 or negative 3 included? Right, so you take the max. Oh. It's not that hard. It's not that hard. It's not that hard. So Then if it's it's 2. And then if you now think of the 4, take the previous subproblem, include a 4 now. The previous subproblem, include now a 4. Let me think. So you include that 4. It's either all 3 adds or it's just 4 itself. Oh my god. Fuck! I understand now. Fuck, I understand now. Okay. A lot of yap. Oh, look at these pipe symbols. I didn't know those were the pipe symbols. Gotta know for next time. Yeah. Okay, let's just call that none. Technically, it should be none, I think. CPI. Colt Gray. I don't know who that is. What the fuck did I just do? Shoot, man. Is less than. Oh. is just that max, or you include it with the previous. So basically you could have done the same thing for, yeah, fuck. Ah, yeah. I love this question, I really do. I do love this question. Okay, let's do a second greedy. Jump game. It's gonna be interesting. Turn this off. Okay. Go check. Let's take like a break. I need to drink some water, check something. BRB. Okay, be right back. I also put on a shirt. Alright. That is me. Okay. What am I looking at? Okay. Let's try a jump game. So you're given an integer array nums, where each element nums I indicates your maximum jump length at that position. Well, that sounds to me like recursion. Return true if you reach the last index starting from index 0, or false otherwise. So if you have 1, 2, 0, 1, 0, first jump index from 0 to 1, then from 1 to 3, and lastly from 3 to 4. So it's true, the second position. True for fourth position. Wait, is this not that easy? Oh, maximum jump, I guess. So 1, and if you jump 1 or 2, well, you can get there. But then you can't jump 1. But you don't know where you jump from. But if you say you can jump to 0, or sorry, that third position, the 2, yes. But then you look at that last position, you can't jump to it. So the brute force approach would just be to jump, 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 you'd kind of like branch by highest value that's in there. So it could be out west, like 2 to the power of, b to the power of d, where b is the largest possible number and d is the array length. Yeah, that's right. But that's not necessarily good. So what do you think here? A thing that I think about with this now is try and think of it in terms of the subproblems. So what subproblems exist? 1, 2, 1, 0, 1. Subproblem, how many steps does it take? Well, it's always true, say at that first position, because that's where you start, right? So maybe that's where we can think about starting to write this DP. So we might say it's false, or maybe we might say we initialize everything to true. Or we can initialize everything to none in the beginning. It kind of makes it more informative for us. And we might say that takes the Leonard nums. And then we might say, okay, for I in range of len of nums, dp of I, so if I is equal to 0, well then dp of I is equal to true, because that's where we start. Okay. And then we would continue. Unless you say like, you just do this. Fuck it. I might just do this. Okay. And then from here, the thought process is, in order to get to false, if this is true, nums I minus 1 it's not necessarily I minus 1, is it? Trying to think. dp then of nums 0 this is how many times you go over, and then you make that false. If you make that false, so those are the ones that you make true though. But what? Then you say from this true position, unless you make everything false to begin with. And then what you do is you kind of branch out to know which paths you can go to. And then if true, yeah, okay. plus j, because j could be 0. J could be 0. Wait, if j is, say, 2, then I has to be also there. So I plus 1 plus j being 0, 1. Yeah. Now j could go out of bounds, right? Good problem, I agree. dp I minus 1. If the last subproblem I think this should be worked from bottom up. I think what I'm doing is kind of wrong. Let me see it through, fuck. So from each of the true points onwards, I should continue. Jumping forward. So for more of the true points, so if it's true, and then you return dp of Leonard nums minus 1. Ah, fuck. We'll see. Ooh, I missed something hard. Okay, yeah, okay. You should try Warden Jug next. All right, we'll have a think. Sorry. If less than equal to, less than or less than equal to, I think less than. Not DP, but a fun DFS math problem. Yo, I can't believe I solved this one actually, just now. Can I just say, I can't believe I solved this one? But it's not even using DP, this one. Is it? I don't know how this is related to DP. Okay, 365, not DP, but fun DFS math prob. I see. I'm just gonna take a look at it, just to suss it out. But firstly, let me see the solution to this, because it worked, right? But also, I wanna go to the jump game, make sure it is actually working, and not just Leetcode being generous. The judging's taking a while. I think I might get a TLE. Yeah, we got a TLE on this one. Oh shit, I didn't need to include this. If it's already here, you know what I mean? Just gonna delete this. Should run the same thing. Ooh, technically, I should do this. Ooh, actually no, I shouldn't. I should just keep it as is. Okay, however, it's not the exact method of solving things. Recursive, DP, greedy. Okay, greedy seems to be like the better option.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve a very popular problem and probably one of my favorite problems of all time. It's jump game. So this is a very popular dynamic programming problem, but it can also be solved in a greedy way. I'm going to show you both solutions, and then we're going to code up the greedy solution, and it's very little code, so that's the good thing, but it's a pretty clever problem, so let's dive into it. So we're given an array of non-negative numbers, so all of them are going to be 0 or positive, and we're initially positioned at the first index of the array. So for example, in this input array, we're positioned at the first index, or the 0th index, right? The first position. So this is where we're going to start. We're going to start in this position. And so for every value in the array, for every element, the number itself, for example, number 2 in the first position, represents the max jump length that we can perform at every single position. Basically, what that means is from...
Let me try and think of an optimization. So right now what it looks like to me is two for loops. 2 for loops. Yeah, I don't see how this. I need
this
inspiration.
first position, we can only do a max jump of 2, meaning our max jump can only get us to this position, right? And another example from here, since this is
Oh, hello, Mohammed. Appreciate your kind words, man. That's what I'm here for.
a 1 value, the max jump we can do is a 1 jump, meaning we can only jump to the next position, right? Obviously this is a 3. The max jump we can do is a 3, meaning we can reach the end position, the 4, from here, right? Because we can do a jump of length 3. Given all of that, given that we're positioned here and that every value represents the jump size, we are only asked, can we reach the last index? So starting from here, given these jump values, are we able to reach the destination, which is the last value in the array? So in this first example, the answer is yes. So we return true because yes, we can reach this position. How can we do it? Well, we start here, so we can do a jump of length 2, or we can do a jump of length 1, right? We don't have to do the max jump length. We can choose to do 1 jump. So then let's say we're at the second position now, right?
It's like a decision. If you have the decision, then if you have a decision, not really clear to me still. Mohammed, when you got your Amazon internship, what was the interview process like? I made a little video on that in the Amazon stream, in the one where I said, I got an internship offer. I think that's a pretty popular video. You can find it on my channel, and I do speak about it a little bit more there. But I won't go into details now. And yeah. But hello, Nahi. Welcome, man. Once again.
Now we're at 3. We can either do a jump of length 1, a jump of length 2, or a jump of length 3. And we're going to do the 3, right? Because now we're here, meaning we're at the last position, right? We're at the last position. Therefore, we did reach the end. Therefore, we can reach the end. So we return.
If dp of len nums minus 1 is equal to true, return dp len, or we just return true. I don't think this is a right optimization that solves it all, but we'll see. Yo. Okay, cool. Let me have a look.
Turn true. Okay, so let's look at a different example. Let's look at this example. Can we reach?
So it actually solved it, by the way. It was just an optimization.
the last position or not, right? That's the question we are trying to answer. Let's brute force this. How can you brute force this problem? Well, let's look at every possible path we could take. So remember, we start over here. What's every single path we could take that could potentially get us to the end? If we find even a single path that can get us to our destination, then we return true. So for each of these values, I'm going to give them an index. So we know that 3 is at index 0. This is index 1, 2, 3, and 4. So these are the indices. So I'm going to start at position 0, right? We're starting at position 0 and see the value we have. The value we have is 3. That means we can make a jump of length 1, a jump of length 2, or a
Decision
jump
tree
of length 3. If we make a jump of length 1, you can see we get to a 2, right? So the next position, if we took a jump of length 1,
yeah, multiple
right?
monitors
so from
right
here
now.
we jump 1, then we're going to get to index 1.
Oh, just my
right?
main
so
monitor and
here.
this one
We're
up
at
here.
index 1. If we take a jump of 2, we're obviously going to get to index 2. If we take a jump of length 3, we're obviously going to get to index 3. So these are the indices, right? So that's what each of these is representing. Each of these values is representing the index. The value on the edge here, 3, 2, 1, these are representing the jumps that we're having to take, right? We're going through all this work because we're showing the brute force solution. So from here, we're at index 1, right? We're at index 1, we have a value 2. That means we can do 2 jumps, right? A jump of 1, which would get us to index 2. So one decision is a jump of length 1, which gets us to index 2, or we can take a jump of length 2, right? Because this is a 2. So then we get to index 3, value 0. So we can take a jump of length 2 and then get to index 3. So now I'm just going to quickly start filling this tree in, and you can see that we're going to be doing a lot of repeated work, and that's what we're going to do. So this brute force solution, I think it's roughly n to the power of n, right? Where n is actually the length of our input array, right? N is the length of our input array. So this is roughly the big O time complexity of the brute force solution. I'm going to show you how to cache this, and when you cache it, you can actually make this a big O of n squared solution, but we need a little extra memory for that. But basically, we're going to optimize this brute force solution. After that, I'm going to show you the greedy solution, which is actually big O of n time complexity, and you can skip to that if you'd rather just do that. So from
Okay, I'm curious if you ever use those hand keyboard things. Hand keyboard. Hand keyboard. Isn't it just a keyboard?
index 2, we see we have a value 1, right? That means we can only make one jump, and that jump is length 1. And when we do that, we jump from here to here, we get to index 3. Funny enough, that's where this path is also. So we're at.
Oh, I'm curious if you ever use those hand keyboard things. Okay, yes. Unless you're talking about yes. So these above 80s. So this keyboard, yes, I do use them. I use them for the Leetcode problems mainly at the moment.
Index 3, that value is a 0 though. So what does 0 tell us? 0 tells us we can't make any jumps, right? We're making jumps of length 0, which means we're not really jumping anywhere. So basically a 3 is a dead end for us. So basically this is a dead end, right? This 3 can't lead us anywhere. And you know, now that we actually go through the rest of our tree, right, brute force, we're going to go to this 3 and we're going to find the exact same thing is true. It can't jump anywhere. So this 3 is a dead end. This 3 is also a dead end. Because when we get to index 3 in our array, we cannot jump anywhere. It has a 0 value. Zeros are always going to be dead ends for us. And we actually only have one valid path left, and that's going to be from index 2. So if we were doing the brute force solution, right, which is what we've been doing up until now, creating the entire decision tree, what would we do now? We would continue the brute force, right? We'd see, okay, at index 2, we have a value 1. That means we can make a jump of 1, right? And when we make that jump of 1, we get to a 3, right? We get to a 3, and we know 3s are dead ends for us, right? We cannot continue a 3 anymore, right? This is what we would do if we were doing the brute force. I'd continue doing this part. But notice we don't actually have to do that because this is not the first 2 that we have encountered. We've already visited index 2 before, right? Look over here, right? Here we visited index 2. And what we can do, and what we found was we actually reached the base case for that, and we found that this was a trap, right? We could not reach the last index when we started at index 2, right? That's what this diagram, this decision tree tells us. When we start at index 2, we cannot reach the end. We get stuck at 3. So what we can do in our memory is DP, let's say we have an array called DP, right? That's going to be our cache. DP of index 2 is going to be false, right? That tells us we've already visited that. We've already gone down that decision before, and it's false because we could not reach the end. So now when we're over here in this position, index 2, we don't have to do anything, right? We don't have to continue that decision of making a jump of 1 and then getting to 3. We can actually immediately stop this, say, okay, no, we know that from here we cannot reach the end. And what you might have noticed by now is none of these paths can reach the end, right? So if we were doing the DP solution or a cache solution, we'd say, okay, DP of 3 is also false, of 1 is false, right? Because take a look at this 1. When you take 1, or rather this one, right? This tells us we're at index 1. Both of the paths lead to 2 and 3, and those are also false. So DP of 1 is also going to be false. And when you look at the root of this, the root tells us when we started at the first position, right? That turned out to lead to all 4 X's, right? We could not reach the end. Therefore, even when we start from the first position in this input array, we can't reach the last position. So DP of 0 is going to be false. We are going to return false, right? That's basically a little bit of the brute force solution, as well as using a cache to speed up the solution. If you do use this extra memory, this cache, you can get this solution to be O of n squared time complexity, but there's actually an even better solution. We can be greedy and we can get a linear time solution, a big O n solution. Let me show you how to quickly do that, and then the code is actually pretty short. Let's take a look. Okay,
hold on.
And we can get a linear time solution, a big O n solution.
Man, I can't wait until I can actually follow along with these vids. I understand like 10% right now. That's alright, that's alright. I mean, yeah. More motivation, huh? More motivation to get into it, huh? Let's go.
Let me show you how to quickly do that, and then the code is actually pretty short. Let's take a look. Okay, so now let's get into the actual greedy solution. So this is greedy, and it's going to be linear time complexity. This problem has a pretty simple solution. We don't actually need dynamic programming. Let's look at we know that this is the starting position, right? The left or the first index is the starting position. Our goal is to get to the end position, right? But let's actually look at this in reverse order. Let's start at the end position and then see if we can work our way to the beginning in a sense, right? So in actuality, the first index is the starting position. This is the goalpost, right? This is the position that we're trying to reach. But we can see, let's work our way backwards. Let's take a look at this position. It's right next to the goal, right? This is our goal, and we're just pretend like this is a goal. So this is our goal, and this is right next to the goal. Mm-hmm. 1 means that we can make a jump of length 1. So really, we go here.
Oh, it is accessible.
And now we're at the goal. What does that tell us? Doesn't that tell us that we don't actually need to reach this position anymore,
No,
right?
we just need to
if
reach
I'm
one.
starting over here,
Yeah.
right? Let's say we're starting over here. This guy over here
Is the
can
guy we wanna
literally reach the end position, right? We know for a fact this guy can reach the end position which we're trying to reach. Doesn't that mean that we can take our goalpost and then shift it over here,
You are
right?
so
because we're
right.
not trying to get here anymore. Now our new goal is to get.
Let me think. The greedy solution is very comes with the realization that our goalpost shifts.
To this position because this can reach the end position, right? So from here, we're now trying to get to this position. We move the goalpost a little bit closer to us. So now we're going to put that goalpost over here. So now let's look at the next position in reverse order. So this is also a 1. That's good for us because we can make a jump of length 1 over here, right? Now, notice this guy can't reach the end position, right? Which is bad, but it can reach this position, which is where our goalpost is, which is all that really matters, right? As long as we can reach the goalpost, we can keep shifting it. So now let's shift the goalpost one more time. We can move it just a little bit closer to our initial position. Now we work our way backwards again. We're at a 3. That tells us we can make a jump of length 3 or less. So it could jump 1, 2, 3 all the way over here, right? That 3 could jump all the way to the end, which is awesome for us, but that's actually unnecessary because we see the goalpost is even closer than we expected. Now it's over here. So it can make a jump of 3 or it can make a jump of length 1. It makes no difference because either way, we can now take that goalpost and keep shifting it. So now the goalpost is over here. We're almost done with this problem. Now we see we're at 2. We can make a jump of length 2 or 1, and then we reach here, right? We reach the goalpost from the first position, right? Therefore, we're moving it one last time to the start position. What that tells us is, yes, we can return true because from the starting position all the way at the left, we are able to reach that end position, right? We're able to reach the last position. So we
Now, what
return
would happen?
true. And we did this in linear time because we're greedy. We kept shifting that goalpost as close as we could to us. And we don't even need extra memory for this. So that's the greedy solution. And we don't have to have a big old decision tree.
And the greedy comes from the realize. Okay. Greedy is also O of n time and O of 1 space. Whereas DP is O of n time and O of n space. Right? No, it's O of n squared time.
We don't even need a cache or anything like that. We're literally just doing this greedy linear time with a loop. Now let me show you how to code it up. It's pretty simple.
Okay, let me think. So this is the greedy approach that we could follow right now. DP approach that I have. I could save that somehow. I will save this and put it here. No! Okay, I need to go to VS Okay, I'm going to retry this with greedy. By greedy, we can think about it like I guess we can think of it as a while loop. While left is greater than zero. There is a math component to this, huh? You could never reach this zero. Sometimes. So the while loop doesn't make sense. The while loop doesn't make sense. Okay. Oh, on my phone. What's real? Food is basically food. Okay. Alright, let me put this back. Okay. Time to have some lunch and I'll be back. 1 sec. Okay. Mm. Wow, goal is equal to I. Wow, that that's actually smart. Okay. Um. Hmm. Hmm. It was. It was. It's basically this. Yep. Very, very, very cool. No. Let's go to VS Code. Intervals. Math and geometry. Bit manipulation. cool that we did a whole section. No, we did. Except I want to do another dynamic programming problem. I need to do way more of these. Okay, I will say though, what have we done? Uber Eats done, Leetcode done, workout then shower. Shoot, man. I want to do one more Leetcode problem before I clock out. All right. I also want. Let's do this now, right? What have I done this year, right? I joined MISC, the club, for next year. I got an internship, made new friends, 100 Leetcode questions. I guess you could say like stopped playing Valorant, I guess you could say. Start living by myself. You know, I did a little bit of that. I am doing a little bit, but it's not permanent. Okay. Yeah, that's it. So I'll have to copy all of this at some point. Okay. Okay. Copy these. Have you done this here? Okay, all of this. All right. Okay. All right. I want to try this last one. I got to do more of these properly. All right. All right. Cool. Let's try. One sec. I just pulled the trigger on the base M4 Pro 16-inch. Let's go. Indeed. All right, bro. Let's go. We've been thinking about it for a while. You were eyeing it for a while, so not bad. Well done. Now you can sit in agony while you wait for the laptop to arrive. Ooh, $400 off. Damn. All right. I'd take that any day. Worth the wait, I suppose. Okay. Let's try this problem. One last problem. I'd probably end up doing more, like, I actually like doing more of these problems. Like today, spending the time doing this, I am happy to spend the time doing this. Makes up for the times that I've not been able to do it. Yeah, what can I say? Alright, fuck it, let's try it. Let's try it. Partition equals subset sum. Partition equal subset sum. You're given an array of positive integer nums. Return true if you can partition the array into two subsets, subset 1 and subset 2, where sum of subset 1 is equal to sum of subset 2. Otherwise you return false. So 1, 2, 3, 4, that returns true, 1 and 4, and 2 and 3. And then 1, 2, 3, 4, 5. Okay, so I looked at this problem before. Like, I've seen this problem before. The question is, whether can I solve it? Alright, we'll see. So, any thoughts on what the subproblem could be? The nums, right? 1, 2, and 3, you can't really make that into a subset. One, 2, 3, 4, 5. Nah, not really. But okay, let's see. Say if you added the 5, sorry, if you added the 4 somewhere. It's not equal subset. No, yes, it is equal subset. So 1 and 2 and 3 is equal subset sum. But 1, 2, 3, 4 is also equal subset sum. 1 and 2 is not equal subset sum. And 1 on its own is not equal subset sum. 3 is equal subset sum. We just include the 3 on its own. And then 4 is equal subset sum. Fojo, do you have another monitor or do you use your laptop screen? I am using my laptop screen and an external monitor. So I'm using both. I'm using one to read your guys' messages and another to type in code. Now, the problem is with this question, I don't know where to start. I'm trying to think of the sub-problem, but also how is this even any sort of sub-problem? Because if you have even, say, 1, 2, and 3, how do you know you can split it in another way to make 1 and 4, and 2 and 3? And if you added the 5, there's no way. What about then, say, let's think about this in terms of backtracking. Not backtracking, but a decision tree. The decision is how many decisions are there possible? When you have two things, the decision is either to merge two things or keep them separate. Ideally, you would just keep them separate, right? And then when you have a third thing, you would either put it in the first or the second. You would put it in subset 1 or subset 2. But you can't exclude it, but you have to put it in subset 1 or subset 2. Well, when you have one thing, you can only put it in subset 1 or subset 2. For when there is 2, you can only put it in subset 1 or subset 2. When there is 3, you can only put it in subset 1 or subset 2. For when there's 4, you can also only put it in subset 1 or subset 2. But you can also rearrange the other subsets. So that's the confusing part to me. How can that work? One thing I do want to do now, kind of write just like, I'm just gonna like write some random shit. Okay. Okay. And then 1, 2. Could have 1 and 2. Say you process them by 1. Firstly, it starts with empty both sides. Then it becomes 1. Or it becomes and then it becomes or just when you see something like this, it's just the same, right? It's like a duplicate. There's a duplicate of this. This is a duplicate. So we can just underline it with 2 or something to signify duplicate. And then you would go 3, so 1, 2, 3. And empty, or 1, 2, and 3. And when you have that, then you think, well, if everything's just on one side, like, you should still bother because you don't know what's on the other end. So you keep them there. Okay, anyway, but this is a tick. Good. And then 1 and 3, 2, or 1 and 2, 3. That doesn't work. And then 1, 2, 3, 4. 1, trying to think. Maybe you encode this to 3 and 3. So if you encode it to 3 and 3, then you might as well. I'm gonna start encoding it. So 3 and 3 becomes 7 and 3, or 3 and 7. 8 and 2, 4, 4 and 6, 4, 5 and 5, or 1 and 9. Five and 5 is correct. And that's the solution true. I don't see how I can make this better. How can I optimize this? Can't think of a good way. I might be stuck here now. Alright, let's have a look at some part of the solution. But I feel like you can encode it like this, in the way that I just did just now. But what does that give me? It gives me a good representation. Um, 2 and right. We wouldn't check the other side because the other side is. I don't see how you would do this any other way. Have a look. Dynamic programming, P, bottom up, TP space optimized, and hash set, and optimal bit set.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve partition equal subset sum. So this is a pretty interesting problem. So we're given a non-empty array of nums containing only positive integers. We want to know if the array can be partitioned into two different subsets such that the sum of each of the subsets is exactly equal. Notice how that's basically saying if we can take one subset of the array, which is going to equal half of the sum of the entire array, right? Because if we partition it into two equal halves, right? Let's say the total sum was 22. If we partitioned it into equal halves, then each of the halves would be exactly 11, right? AKA, one of the partitions is going to be
You're already
half
getting
that
straight
of
into
the
one of the
total
optima.
sum. So for example, in this problem, the sum is exactly 22. So we want to know, can we get a partition or can we get a subset of this array? Basically, we can choose any of the values.
Oh wait,
and
why don't I also consider taking a look Oh, there is no hints. Okay, there are no hints on this.
can we get a subset such that it sums up to 11? In this case, the answer is yes. It's true because we can take, the single 11, that sums up to 11, right? And obviously, if there's one way to get half of the sum of the total array, then the remaining elements are going to basically equal 11 as well, right? So you can see that 1 plus 5 plus another 5 is going to be equal to 11, right? Basically, these are the two partitions. So as with many problems, let's just try to figure out what the brute force solution would be. So basically, let's start at the first element, right? And for every single element that we visit, we have two choices, right? We can either include this in our sum or we can not include it in our sum. And we want to basically determine every single sum that we can make with any single subset from this given array. And we want to know, does that sum ever equal 11? Because 11 is our target, right? If we sum this up, divide.
Holy shit. Why is this so right? Wait, subset sum. This is so right. Darn, this is like a whole different level. You have to process it. Okay, well, let's look now. Trying to get a target of 11. Or sorry, trying to get a target of 5 in this case. So if your target is 5, it's like a fucking simplification of the problem that makes it so. Okay. I didn't realize you could simplify the problem like this. It makes it so much easier. So now that you have one or to exclude or include, you can think of including, exclude to get a target of 5. Alright, so if that's the way we think about this problem now, got 1, 2, 3, 4. You can either include or exclude. So it starts from 0. Include or exclude the 1. You get 0 or 1. Include or exclude the 2. You get 0 and 2. Include or exclude the 2. You get 3 and 1. So include 2. 1 and 3. Include 3. Include, exclude, so include and exclude 5. Wait. And then you include the 4. Okay. Okay.
Divide it by 2, we get 11. So we want to know if that's possible. So let's brute force it, right? So the first choice, we can either choose a 1 or choose nothing, right? Basically skipping that. So either our sum will be 1 or our sum will be 0 because initially our sum is 0. So the next value is 5, right? So basically for each of these paths, we can choose 5 or not choose 5. If we do choose 5 here, we'll get a 6. If we don't, we'll stay at 1. Otherwise, on this path, if we choose the 5, we'll get a 5 because we started at 0. So if we skip the 5, we'll stay at 0. Next, we get an 11. So basically continuing that, right? So I don't know if I'm going to have enough room for this. Okay, no, 11 plus 6 is going to give us 17 on this path. Clearly, we went over, so we would probably not want to continue down this path. But over here, if we skip the 11, we'll get a 6 still. If we take 11 here, we're going to get 12. If we skip it, we'll get 1, and etc. etc. We'll get 16 here. Skip, we'll get 5. If we take 11 here, we'll get 11. Skip, get 0. But clearly, we found our target that we were looking for. We don't really have to continue anymore, right? So basically, we can skip this last element. We found our target. We're going to return true, and we're going to go back up. So as you can tell, since every level of our decision tree, we're having two choices, right? And what's the height of this decision tree going to be? Basically, for every single element, right, we're going to have a decision. So let's say the input size of the array is n. So basically, our time complexity is going to be 2 to the power of n if we do a brute force method. So let's go back to the first step, basically the first element that we were at, and let's see if there's any repeated work that we can cut down on. So initially our index or our I pointer is at the first element, right? So basically we're at the beginning of the array. We can go down the entire array. We can choose any elements from here, and we want to know, can we sum up to the target 11? Now, once we take our two paths, right, we're basically going to say I is now going to be shifted to the next element, 5, right? And we had two choices. We could have either chosen the 1 or we could have skipped the 1, but clearly now we have a new subproblem. We already have a 1, so from the perspective of this decision, we're not looking for a target of 11 anymore, right? We're looking for a target of 10. We're looking for a target of 10, and not only that, but initially our I pointer was here, meaning we could have done the entire array.
That's
but
the
now our I
subproblem.
pointer is over here, so we're not even looking at the entire array anymore. We're looking at a subarray, basically the remaining elements of the array minus this first one. So if we were to cache this, our new subproblem would be target of 10 that we're trying to solve, and I is not at 0 anymore. Index is at 1. Similarly over here, we can see since we're at 0, the target is still 11, right? We are trying to sum up all the way to 11, but the index that we're starting at in this case as well is 1 now, right? Because we basically said we were skipping this element down this path, right? So now we want to know, is there a way that we can sum up to 11 basically just from this subarray, right? And every time we made a decision, we would continue to update these values, target and I, right? So as you can see, what are the dimensions of our cache going to be? If these are the two variables of our cache, what are the dimensions going to be? Well, clearly I could be any value in the input array. So the dimensions of our cache are going to be n, where basically n is the size of the input array, right? Because I could be at any value from 0 to n minus 1. And what about the target? Well, the target is basically the sum of the entire array divided by 2, right? So basically sum of nums divided by 2, or, you know, the constants usually don't matter in time complexity. So basically this is going to be the big O time complexity. Now this is technically better than 2 to the power of n because they do give us a pretty good limitation. Like the values in this input array are usually going to be, I think, less than or equal to 200. Now if they were really big, like if this could have been 1,000,000, clearly that would not be very efficient because our sum could have potentially been super large. But this is basically the best way that we can optimize it. So basically, if we did a depth first search solution with a cache, like a backtracking solution with a cache, this would be the time complexity, and this would also be the memory complexity because this would be the dimensions of our cache. But it's actually possible to improve the memory complexity a little bit with dynamic programming, and the time complexity is mainly going to stay the same as this, but the overall memory complexity can be improved. And let me show you why that's the case. So suppose we were starting at this first value, right? And let's say we already knew all the possible sums that any given subset from the remainder of this array. Like basically what we could do is say for every single one of those sums, we would add 1 to it, right? So for every t, let's just call it t for now, in that subarray, we're going to basically be checking two things, right? Either if t is equal to target, right? Like some possible sum from this subarray totaled up to the target, then we would return true, right? Every possible sum that we could create from any subset in this subarray, and if it basically that's what t would be, and if that t happened to be equal to the target 11, then we would return true, right? Or if we took every single sum we could create from this subarray and added 1 to it, basically 1 because that's the only value left over here, right? 1 plus t equal to target. If that was also equal to 11, then we would return true as well, right? So basically, this is the recurrence relation that I'm trying to show you. And so this is basically the idea we're going to use for the bottom-up solution. So instead of starting here, we're going to work our way backwards. So we're
all right. The bottom-up solution. I want to try solving the bottom-up solution. If you ever want to screen share your iPad when writing, you should get Lonely Screen free. Lonely Screen. Let me have a look. Oh, I see. Interesting. I do have one alternative already that's different. But keep this in mind. Keep this in mind. Okay. All right, let's see. So let's try and think about this as a bottom-up approach. For itself is problem where the target is 5. Can't get it. So next you include 3. 3 to not include it. Or you include it and exclude the 4. I mean, if it's all strictly increasing, doesn't matter. Perhaps it doesn't matter. It would get you 7, but then, well, you know, you realize the 2's there. So you're fine. Okay, let me try and DP this. Let me try and DP. So I'm trying to DP this from which direction? I'm going in the opposite. Hmm. Hmm. DPI. If we're going backwards, right? It means we start from that say 4. And 4 is going to be our max value there. Got to keep track of what our target is. So our target is equal to, so it's going to be sum of nums div 2. Yeah. The problem is, so if if it's not divisible by 2, right? If sum of nums is not divisible by 2. So if the floor of this, sorry, if the mod of this so 0, 1, 0, 1, 0, 1. If this is equal to 0, then you can continue. But if it's not equal to 0, if it's equal to 1, and you would return false. Just impossible. And then otherwise you would know what the target is. And then dp of if this nums is greater than the target, if it's still less than the target, then you can continue. But what do you mean by continue, right? What do you mean by continue? The nums I is what? It's that value 4, which is less than said target 5. If it's less than that target, then you know the DP value for I is going to equal to nums I. Now this is plus the DP of I plus 1. Oh shit. Yeah, no, this is fine. So 1 dp of I plus 1, else dp of I is equal to num. Agree or disagree? What if it's less than or equal to? If dp of I is equal to target, return true. Oh, so if you never reach that stage, you return false, right? I think. Would you return false? You never find it? Right. I think that's right. But this isn't right. So or you don't include it. I have to see. I don't think this is entirely correct, but we'll see. Nums plus I. Let's see. I put false when it was meant to be true. Got 6, half 3. So you go from 1 plus 1 plus 2 plus 2. Yeah, that wouldn't be right. I fucked that one up. 1 plus 1 plus 2 plus 2, that's not right. So one let me think. It's just this middle condition that I need to change. Just this middle condition that I need to change. What's happening and what's wrong in my thinking? So if I were to think of this again, you check the 1 1 and 1 is less than 4. Sorry, less than 3. Yes. Then how do you move to 2 and 1? So think about the subproblems again, right? So 1 okay. If it was just 1 1, then you'd want to return. I know. I can kind of see where I went wrong. I can kind of see where I went wrong. I didn't consider this target during subproblem. So this target should be within the subproblem, not outside of it. So if that's the case, right, the target okay. Let me think. What's the DP value inside? It's the current value or current sum, current sum. Current best sum. Yeah, it's the current best sum. current best sum that is closest to this target. Current sum that is closest to the target. Or it's the sum that is closest to the target. But not necessarily. It's just sum. Less than the target. Sum less than the target. Yeah, it's just some sum less than the target. Wait. If it's some sum less than the target, that not be problematic? So if you had 1, 1, 2, 2, right? The subproblem where you had 1, you go 1 in target being nothing. So your DP is going to be 0. The target is non-existent. Wait, why would the target be? You can't half a 1. If you had targeted 2, so what, it'd be, say, none. Target is none. There is no target. And the DP value is 0. DP sum is 0. And then you might have the next DP. Maybe this is worth writing, right? I want to think this through. One, 1, 2. So you kind of like from here to here. One times 2 plus 2. All divided by 2. If this is equal to the next value. Shit. Oops.
Start here. So, and this is very simple, right? So how many possible sums could we create from this subarray? Well, there's only one value here, right? We either take it or we don't. So the amount of sums we can create is going to be 0 or 5. And what I'm going to do is I'm going to be storing these values in a set. So let's say this is our set. So far we have 0 and 5. Next, what I'm going to do is I'm gonna go to 11, right? We're going to work our way backwards. I'm going to start at 11, and I'm going to iterate through every single one of these, and I'm basically going to add 11 to them, right? So for 0, let's add 11 to it. That's going to be 11. I'm going to add that to our set. Let's look at 5. That's going to be 11. I'm going to add that. 11 plus 5 is 16. I'm going to add that to our set, right? Clearly, we can see we already found the target value, so we could return, but let's just keep going to see all the possible targets we could create with this input array. So we were done visiting 11. Now let's go to 5, right? So basically, we're going to iterate through every single one of these, add 5 to them, and then see if that's a new value. If it's already a value that exists, then we wouldn't do anything. Like in this case, we can see 5 plus 0 is just going to be 5, right? So I'm not going to add a second 5 to this because we already have a 5.
Yep.
This is a set. It's going to want only unique values. So we're not going to end up adding a second 5. But if we add 5 plus 5, that's going to be a 10. If we add 5 plus 11, that's going to be a 16. We already have a 16. If we add 5 plus 16, that's going to be 21. And basically, I'm going to do the exact same thing with 1. So, we would add a 1 here. We'd add a 6. 5 plus 1 is 6. 1 plus 11 is 12. 1 plus 16 is 17. And 1 plus 10 is 11. We already have 11. 1 plus 21 is 22. So basically, this is the entire list of sums we could possibly create from our given input array. As long as this set contains 11, we return true. If it doesn't contain 11, that means it's impossible to sum up to this target, so we would return false. Now, I think in practice, the size of the set is probably going to be about the same size as the cache that we would use in the memoization technique, but technically the size of this cache is going to be limited to the size of the target, which is basically limited by the sum of the nums input array. So this is going to be the memory complexity in this case. Technically, the time complexity is going to be the same. But I think this solution is definitely easier to code. It's just a little bit tricky to actually arrive to this solution.
Definitely.
I think going through the brute force to the caching to the dynamic programming solution is the best thought process to arrive to this optimal solution. So now let's jump into the code. So one thing I didn't mention
Hold on.
is that if the sum of our input array is odd, then it's obviously going to be
Interesting. So we maintain a set, which is not what I believe to be a DP, but it's like a DP. Zero to one knapsack. The fuck? Thoughts on taking DSA course while doing discrete math at my actual school? DSA would be some online course. If you think you have time for it, yeah, do it. I don't see the downside of it. And you don't need to worry about, say, like the effectiveness of doing DSA while learning discrete math. Like, there's so minimal of a difference for you to even need to consider that aspect. Where, say, you know, you need to do discrete maths first before doing DSA. Versus just doing discrete maths with DSA. So, I just do it if you want to, and if you have the time and the mind space to do it. Definitely. So is this a 2D array? Whoa. Shit, how did... Hold up. The flip. Why does this seem like a 2D array? This is pretty cooked, hey? Use a set for sure, I think. But you're not really using dynamic programming. That's the biggest alarm that I see. Oh, let me drink some water here. Whoops. Ooh, shit. That was loud. Yeah, I'm fortunate to have all data. Sometimes it's bad for things because I can't. It's a bad thing though because I can't decide what to work on and procrastinate. Yeah. Fair enough. Set a routine. Don't need to decide. You know what I mean? Set a routine. Every morning you do your discrete math, and then every afternoon you do your DSA. No decisions necessary. Perhaps that is one option. Right, so say we use a set, right? Ops.add 0. Opt in opt. Opts. Add I plus opt. I plus opt. So I being nums I opt. If target in opts return true. This is interesting because you don't use DP at all. That changed size during iteration. For sure. Set change size during iteration? Well, what you can do is you just list. Well, that worked. So this was the way that was talked about here by Leetcode. But it's not the solution I want to use. Yep, I recently read The Power of Habit and it talked about routines. I'm definitely going to do that. Yeah, perfect, man. I would even say like, what was it? I read part of that book, or it's been some time now since I read that book, but yeah, like I agree with everything that was said in that book. And yeah, it's just like habits are just a double-edged sword, I would say. You know, depends on the habit is really what makes it a double-edged sword. Okay. So look, this was done using sets. Now, it's not necessarily the way that I would have wanted to get this problem done, but we got this problem done anyway. Let's call this, what's this called? Partition equal subset sum. Okay, it reminds me also that I actually have to do something. Hello, Zero Anims. Do you have a job now? If you call my internship a job, yes. Visual Studio. Gotta bring this up always. That's a dynamic programming problem. Yes, it is. You are correct. Okay, nice. Do you participate in Leetcode weekly contests? Not really. I just do this Leetcode. Maybe I will when I finish Leetcode 150. The problem is, yeah, it's still taking me a long time to finish all this. Okay, let's see. So no, the fact that it's so fucking slow right now. $4.16. Okay. It's such a good question, this one. Oh. And this problem you have to break down the problem into finding a subset sum equal to some target. Okay. Okay. Real. No, I know. The agony Okay, let me turn on the heating, the fan. Yeah. The DP approach, I think the way he'll approach it here is
impossible to partition it
using
into
the
an
set.
equal half, right? So basically, if the sum of this
We'll just see it.
2 is 1, then we're gonna return false. Also, I'm going to have a DP set, as I mentioned, because this is going to be the most optimal solution. To the DP set, I'm just going to add a base case of 0. Basically, we're guaranteed that we can add up to a sum of 0, right, if we just don't choose any elements from the input array nums.
So you're just making...
And the target that we're trying to sum up to is,
making
of
the
course,
DP the set.
sum of nums divided by 2. So with that being said, let's iterate through every single value in nums.
Does that
in
make
reverse
sense? I
order.
guess
You
it
could
does.
do it in regular order, but I'm just going to do reverse order because I'm used to it. So we're going to go through every target or every total value that's already in our DP set for every t in DP. And what we want to do is to DP add a value, right? We basically want to add t plus nums of I, right? Because I is the current index that we're at. We want to add, for every single t that's already in DP, we want to add nums of I to it, right? But we can't update this DP set while we're iterating through it. So what I'm going to do is create a new DP set, basically next DP. It's going to be the DP set that we iterate through over the next time we execute the loop. So instead of adding to DP, what I'm going to do is add to next DP. But we also don't want to lose all the original values that are in DP. So what I'm also going to do is to next DP, I'm going to add the t value as well, whatever the t value happened to be. Now, if I really wanted to, I could probably skip this line if I just took DP and cloned it and then set that to next DP, but, whatever you prefer. Basically, what I'm doing is I'm setting next DP, I'm taking every value in DP, adding it to next DP, and also adding this t plus nums of I to next DP. And once this loop is done executing, we're basically going to update, reassign DP to the next DP set. And this is going to keep executing. It's going to keep executing. I is going to start at the end. It's going to go all the way to 0. So then we're going to have gone through every single one. And at the end, we can return true if and only if the target happens to exist in DP. Else, we have to return false. And yeah, so this is the entire code, and it runs fairly efficiently. So this is about 50%. Now, I think it would probably be a little bit faster if, the first time we find the target value, if we just returned it. Actually, let me just, you can probably stop watching at this point. That was the entire solution, but let me just see if this actually does speed it up. So let's say if I happens to be equal to the target, we can immediately return true. Let me see if that does speed it up. Okay, so that actually did. So it's about twice as fast. I think the old one was 14 milliseconds, so this is 600 milliseconds. So this might be an optimization that your interviewer would like, but the overall time complexity is still the same. But I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
I agree with this statement, Mr. 6462. Oh, come on, it's alright, man. Same as me. So look, I guess ops becomes DP, and we use a DP for ops in DP. DP. Ah, fuck. I guess this is it. Okay. Nice. How does this bot up approach com look like? Hmm. Hmm. So look, it's false. For it's like a 2D DP. So it's false. And it's initialized to true for only the first column. Right, for the first column, yeah. Because why? Because no. Have you heard of O1's knapsack? No, I haven't. Although I will have to read into it. Thank you for reminding me, that is. Nums I minus 1 is less than or equal to j. EPN target. Yeah. No. Can't think of it much further, but okay, knapsack. 0-1 knapsack. I'm gonna get some water. Go back. You can see how this is. I need an explanation of knapsack.
Hey guys, here's my dynamic programming tutorial with the 01 knapsack problem as our example. Let me explain what the knapsack problem is first. We have a certain number of items. Let's say we have n items, or 5 in this case, 5 items, and each item has an associated weight and value with it. So the first item weighs 1 kilogram and is $5, and the second item weighs 2 kilograms and it's worth $3. And the problem is we're trying to decide which items to put in our knapsack, which can only carry a certain amount of weight. Let's say 10 kilograms. We can only carry 10 kilograms. And we're trying to maximize the total amount of value that we carry with those items. So for each item, we're going to decide kilograms. Items to put in our knapsack, which can only carry a certain amount of weight. Let's say 10 kilograms. We can only carry 10 kilograms. And we're trying to maximize the total amount of value that we carry with those items. So for each item, we're going to decide, do we put it in the knapsack or outside the knapsack? So let's just say yes or no. Or we could write it as 1 if it's in knapsack, or no if it's not in the knapsack. And at first glance, it looks very hard because if we make this decision for every item, the total number of solutions, the total number of potential solutions is going to be 2 to the power of n, or 2 to the power of 5 in this case. But actually, we can do much better than that with dynamic programming, and you'll see how you can do it in a second. Here's a common procedure in dynamic programming. We first come up with a recursive solution, and then we memorize or store some of the intermediate results to make it run faster. The third optional step is coming up with a bottom-up approach, but I'm not going to do that just for simplicity's sake for this particular case. So here's our naive recursive solution. The idea is we're going to start with the last item, and we're going to move down the list. And we ask ourselves for where the pointer is, are we going to put this item in the knapsack or not? So for the first element, of course, that's yes or no. And we'll also keep track of how many items we have left to consider. Or you can see as the position of the pointer as well. So it starts with 5, and we'll keep track of the amount of capacity we have left. That starts with 10 in our example, 10 kilograms, and the value we have so far. That starts with 0. And if we said no for the first item or the last item, this item, then n becomes 4. We're essentially moving this pointer to the left. So that becomes 4. And C, capacity doesn't change, so that's 10. And the value doesn't change, so that's still 0. And if we said yes, n becomes 4. We have 4 items left to consider. The capacity becomes 10 minus 5 equals 5. We can still carry 5 kilograms. And the value becomes 0 plus 2 equals 2. And for each decision, we ask ourselves, for the fourth item, are we going to put this in the knapsack or not. So that's yes or no again. So we keep repeating this process until we get to the last item, this one. So that's the idea behind our recursive solution, but it works slightly differently in the code. So let's see how that works. So here's how our recursive solution works in our code. We define this function ks, knapsack, that takes two variables. The first variable is the position of the pointer that we're looking at, or the number of items we have left to consider. And the second variable is the amount of capacity we have left. So the first call for this example is going to be ks of 5 because we have 5 items left to consider, and 10 because we have 10 kilograms in our capacity. And here's our base case. If n equals 0, that means we have no items left to consider. And if c equals 0, we don't have any capacity. So we just return 0. And from this function, we're returning the optimal value that we can achieve with this pair of variables instead of the list of items itself. So if you want to do that, you'll need to change the code a little bit. Now, if the current item's weight is larger than our current capacity, then we can't put it there. So we just move the pointer to the left and we call this function again. And if that's not the case, we'll try both putting the item in the knapsack and not putting it there. So if we don't put the item in the knapsack, then we just call the same function with the same variables again, with the pointer moved to the left. And if we put it there, we'll count in the current item's value and we'll add it to this recursive call where the pointer is moved to the left and the capacity left is reduced by the current item's weight. And we'll just take the maximum one of those to get the optimal value. By the way, our values are stored in this array that starts with a dummy variable and our actual values. So that's 5, 3, 5, 3, 2. And the reason is because when we have, say, the second element, we can just call v of 2 and we get the right element, the right value. And it's the same thing with the weights. So it also starts with a dummy variable and then actual weights. So this is how our solution works, but it's very, very slow. And let's see why that is. If you think about the worst case scenario, we try for the last element, we'll try yes or no. And then for the second last element, we'll try putting that item in there and not putting it there, and so on. So we're basically trying every possible case. So the time complexity for this algorithm will be exponential, which is very bad. Dynamic programming says we can do better than that by memorizing or storing some intermediate results, or by noticing that there are some duplicates in our computation. So here's how we can do it. We have here a function that's almost exactly the same as what we had earlier, except for these 3 lines. And the first thing to notice here with the previous function we had is that there are only n times c possible variable pairs that we could have. So in the example we had earlier, this would be just 10 times 5 times 10, which is 50 possible variable pairs. And what we're doing here is we're storing the results of this function in a 2-dimensional array with the height n and width c. And we initialize it to undefined, the outside function. And then when we call this function, if the result is already stored for that particular
I can see how that is.
then we just return that instead of going through the whole thing. And if that's not the case, we'll go through the whole thing, and before we return the result, we'll store it in the array so we can reuse it later. So what's the runtime for this function? The first thing to notice to find that is that we reach this line only at most n times c times. So we go through this whole thing at most n times c times, and every time we go through this function, the maximum number of recursive calls we make is just twice, in this case, this one and this one. So the maximum number of times we call this function itself is about 2 times nc, or just an order of nc. And the time it takes to execute each call, or time per call, is just a constant time. So the total amount of time it takes to execute this whole thing is just an order of nc, which is much better than the exponential time complexity we had earlier. Alright, hopefully you liked the video. You might also
Okay.
like my other video about dynamic programming with
It's a good explanation
CSS
on
as our
dynamic
example.
programming altogether.
And if you want to watch more videos like this one,
I
you
do
can
appreciate.
subscribe right here. And see you soon.
Okay. Okay, I'm gonna call it now. Save. Trying to think. So I need to do some workouts later. Look at the design doc. Alright. There is a 1D optimization. Nah, I can't be fucked thinking about it. Alright. Nah, it's good. But maybe it's something I think about later. I think definitely for this question, it's something that I might. Like all dynamic programming questions, I should start, but like, ones also. Good rest of your day. Also, Nahi, appreciate you. And Merry Christmas indeed. Alright. Alright, I'll call it a day, guys. Thank you for joining. Appreciate it. And I hope see you guys later. Alright, peace.